Okay, good morning. Good morning. Get my microphone here. Try again. Good morning. Thank you. Did you get to see the eclipse last night? That was pretty cool. When it started, where I was, the cloud was covering the whole thing. I couldn't see a thing. But luckily, right after it turned red, the cloud just went away. So I got to see the best part of it. So that was pretty cool. Okay, let's move on with 7.4. We're going to look at how we can do integration by partial fraction today. We're going to look at the simpler of the four cases today, the two simpler cases. Okay, so let's see what's the point of doing this. Let's compare these two integrals. When you look at this integral here, upon first glance, it looks like we might be able to do a substitution to take care of this. Let's see what happens if we try that. If I let u be the more complicated part, the one that's in the denominator, then du, of course, is 2x minus 7 dx. So this stuff down here, of course, is u. And whatever's left here somehow has to turn into du. We probably could do it, but it's not a very straightforward thing to do. It's quite complicated, as you can see. I need 2x minus 7, but all I got is x minus 8. How do I turn x minus 8 into 2x minus 7? I can't just multiply by 2, because then I'm still off by one number somehow. So that's not easy to do. However, so trust me on this, that we can break this into two simpler fractions. So this guy turns into that. And you can verify this very quickly by finding a common denominator and multiplying them back together. And the result here is that we get a simpler integral to worry about. We got two things in here. Each one is a simpler fraction, right? Oop, that's an x, sorry. So let's break that into two things here. Do you remember what the first one turned into? Right, 2 times the natural log of the absolute value of x minus 2. So how do you do that? In here, you let u be x minus 2, and du, of course, is then dx. So this is 2 over u times du. I think my microphone's acting up. Right, and then the second one here, same idea, natural log of x minus 5 plus some constant. try. Technical difficulty, sorry. Can you hear me? Yep. I think microphone's cutting in and out. I don't want to hold it. Okay, so anyway, as you can see, if we could break down this complicated expression into two simpler ones, then we could integrate them easily. This step right here, this is called a partial fraction. Expansion. Okay, so then we're going to concentrate on how we can do this, how we can break this thing that looks pretty bad into two simpler ones, and then we integrate using natural log. Okay? Okay, so let's go back to what we started with. X minus 8 over x squared minus 7x plus 10. First, notice that we can factor the denominator. We can break that down into x minus 5 and x minus 2. And this is the first case, the simplest of all these cases. We'll call that case 1. Case 1 is when the denominator is a product of distinct linear factors. Okay, distinct means it's not repeated. Linear means it's up to the first power, right? X minus 5, x minus 2, the power is 1. So here's what we do. We're going to say that we can break this down into two fractions. One is some constant over x minus 5. We'll call that constant A. The other one is some other constant over the other factor. Call that B. And A and B are constants to be determined. Okay, and that's how you handle all of these case 1 things. If the denominator is a product of distinct, not repeated, we don't want to see x minus 5 and x minus 5. We want them to be distinct, not repeated. And also we want them to be linear factors. We don't want x squared minus 5, for example, or x squared minus 2. Then we multiply both sides by x minus 5 times x minus 2. And left side, of course, is x minus 8. The right side, a over x minus 5 times x minus 5 times x minus 2 gives me a times x minus 2, right? Then the other one is b over x minus 2 times these two things. The x minus 2's cancel, and I get b times x minus 5. Now we figure out a and b. Whatever's on the left must be equal to whatever's on the right. That's what the equal sign says. So multiply this out. We get ax minus 2a plus bx minus 5b and then we get a plus b quantity times x. Here's my ax, here's my bx. I put them together like that. And then I got two things that don't have x in them, minus 2a minus 5b. And the left side is 1x minus 8. Okay, you see how this works now? We want these two to be equal, right? So this means that 1 must be equal to a plus b, whatever a and b are. And negative 8 must be equal to minus 2a minus 2b, minus 5b, sorry. Okay, and how do you solve for this? How do you solve for a and b? Yeah, that's one way. What's another way to do that? Right, we can solve for b in the first equation, sub into the second one, right? There are different ways you can do that. One way is to multiply the top by 2. And then add these two equations together. So we get negative 6 is equal to 2a minus 2a, the a's go away. 2b minus 5b is minus 3b. So b is equal to 2. See that? Or what we could do is say a is equal to 1 minus b, and then sub into the second equation. So you're solving systems of equations, then there are various ways to solve for them. Okay, now I know b, I know a too, because I know a plus b must be 1. If b is 2, then what should a be? Minus 1, right. Questions so far? Okay, so now we found out what a and b must be. So this and that, right? So x minus 8 over x squared minus 7x plus 10 we said this was a over x minus 5 plus b over x minus 2. And now we know a and b. Okay, so we accomplished what we wanted to do. We wanted to break that into two simpler fractions. Each one could be integrated very easily, whereas the original one is not the easiest thing to integrate. Questions? Does that basic idea make sense? Yes? Good. Now let's try another one. Here we have 1 over x squared minus 4 dx. And we like to integrate that. When you look at this thing here, first, always check if you could factor the quadratic down here. And it's a difference of squares, so we can factor that. So this is equivalent to 1 over x minus 2 times x plus 2 times dx. Okay, now we're going to expand this thing, 1 over x minus 2 over x plus 2, and then we'll come back to the integration. And what do we want this to turn into? Look at the last example. What do we want this to turn into? Good. A over x minus 2 plus b over x plus 2. And again, a and b are constants to be determined. Okay, now I want you to take 3 minutes, follow the same procedures we did in the last example, and find out a and b. And while you do that, I'm going to mess with my microphone. All right, who got an A and a B? What'd you get? Which one's A? Negative 1/4 and B? Do you agree? What else do you have? Who has another answer? You have A and B in reverse, okay. No. I had them reversed too. Oh, that's funny. Okay, let's find out which one it should be, okay? All right, so let's go to a new page. All right, so here's what we're trying to do. We're doing 1 over x minus 2, x plus 2 equal to a over x minus 2 plus b over x plus 2. Okay, and then we multiply both sides by x minus 2, x plus 2. And left side, of course, we get a 1. And right side, we get a times x plus 2, right? The x minus 2 will cancel. And b times x minus 2. Rewrite the right-hand side a little bit. We have a and b both multiplied by x. And then the terms without x, we have 2a and minus 2b. And left side is 0x plus 1, right? So therefore, a plus b, the x term must be 0, and 2a minus 2b must be 1. And let's solve this one by using substitution. We see from equation 1, b is minus a, and then we'll take that into the second equation. So therefore, 4a is equal to 1, and a is equal to 1 over 4. And b is the same as a, but the sign is reversed, so b is equal to negative 1 over 4. Questions? Yeah.
I basically did the same thing that you did, except I had the 1 over x plus 2 times x minus 2. Is there a reason that's wrong? Because I got the same answer with the first guy, where a and b times.
You had 1 over, instead of 1/4, you have 1.
No, I had a, I had the same answer with the first response. I had a minus 1 over 4, b is
If you broke this down into a over x plus 2 and b over x minus 2, the order doesn't really matter.
Yeah.
So if you do that, then you would get the other one.
Would the first answer be wrong then?
Well, how would you check that? Is there a way to check that? Yeah, you could plug them in and add them together, see if you get the same thing that you started with, right? So when in doubt, check it out. Ha. Oh boy. That was not planned. I don't plan for those things. Okay, we're not done with the integration, right? So let's go back and finish the integration. So we found out that we could break this down into 1 over 4 times 1 over x minus 2 minus 1 over 4, 1 over x plus 2 dx. Okay, and let me show you how to do this by substitution in case you forgot how to do it. Second one, I don't want to reuse u. I'll use w for the substitution. The first one is, of course, 1 over u du with a 1/4 taken out to the front. Second one, same thing. So we get 1 over 4 natural log of the absolute value of u minus 1 over 4 natural log of the absolute value of w and some constant. Okay, and then you put the u and w back. And there's the answer. Question?
So before, I'm a little confused as to why you can say that the term a plus b times x is equal to 0.
The previous page? Okay. See, the right-hand side is a quadratic, second degree, right? The left-hand side is a constant. I'm sorry, the right-hand side is a linear function, first degree. The left side is a constant, 0 degree. So the left side has no x. But whatever's on the left must be equal to whatever's on the right. So therefore, these two guys together, when I add them, they must vanish so I can get a 0x on the left. Yep. And then whatever's left here must be 1.
So how do you know that x is equal to 0?
Say that again?
You say a plus b equals 0. How do you know x is equal to 0?
Oh, because x is not a predetermined number. It could be anything. It could be 0, but in general, it's not 0. Like in the integration here, if x is 0, then this is meaningless. But it's not 0 in general. That's the whole point of integrating this thing here. But that's a good question. Why is x not 0? It could be, but it in general is not. Hey, by the way, can we rewrite this in a different way? How would you do that? Right. So, yep. So we could do this. Factor the 1/4 out. And we know ln of something minus something else can be turned into 1 log the first over the second. Right? Remember that? What if this is addition instead of multiplication? I just said the answer. What if this is addition? Yes. Yes. Then this will be multiplication, right? Okay, good. Okay, so that's case 1. Let's look at case 2. If you get case 1, case 2 is not terribly difficult. And on Wednesday, we'll look at the more difficult cases 3 and 4. So case 2 is the denominator is a product of linear factors again. But this time, some of which are repeated. Here's an example. Ten over 5x squared minus 2x cubed. First, you look at the denominator here. There's a common factor of x squared. So let's take that out. And we want to look at the x squared as x times x. And there's my 5 minus 2x. So these, again, are first-degree linear factors. And this time, x is repeated. When you break this down, we still get some constant over x. But then we notice that x is repeated. So we get one more constant, but over x squared. Okay? So this is what you get when x is by itself. This is added in here because x is repeated. And then we have the last one here. C over 5 minus 2x. And can you guess what you would do if this is x to the third power? You get another one. You get d or c over x cubed, right? Each time it's repeated, you just keep on adding another one. Okay? Okay, we're going to leave the constants alone. I want to concentrate on the form. So let me write out the case I just talked about. Okay, so let's try this one. 10 over x cubed times 5 minus 2x, and that thing is squared. So here we see x is repeated, shows up 3 times. So the first thing you get is whatever x would give you normally, a over x. And then take care of this, the second time it shows up, b over x squared. And then one more time, c over x cubed. And then it's 5 minus 2x's turn, so d over 5 minus 2x. And last one, e over 5 minus 2x squared. Does that make sense? So however many times this thing repeats, you just keep adding these terms. Now solving for the constant, it would be a headache here, right? If we have time and we're really motivated to do it, we could do it, but I don't want to do it. But you do exactly the same way. You multiply both sides by this denominator. Let's just carry a few steps out. We're not going to do the whole thing, but just carry a few steps out. Just a few steps. So a over x times this gives me a x squared, 5 minus 2x squared, right? And then b over x squared times that whole thing is b x 5 minus 2x squared. And then c over x cubed times that is c 5 minus 2x squared. And then d times what? Times x cubed. And how many of these? 1. Yep, 1 factor of that. And finally, e x cubed. Yeah. This thing here? This one? Yes. Yeah, 10 over all of that stuff. Yeah, you're right. And then, but this one is right? Okay, so, and you could solve for the constants if you do this carefully, but we're not going to ask you to do this on the exam or quiz, right? This is too much. We might ask you to do something like in the last example, but nothing this extreme. Questions? Let's do one more with this thing. Again, we'll just concentrate on the form, but not the constants themselves for now. All right, so take 2 minutes and break this down. Don't solve for the constants, but produce a form that looks like that. Okay, so this is another one where if you were to solve for the constant, it would be pretty difficult. But getting the form itself shouldn't be too difficult. So first notice we could factor the x squared minus 9, break it down like that. They're still raised to the power of 3. And therefore, each of those gets a power of 3. All right, so now what do we get? A over x plus 3, right? And then, right, b over that thing squared. Any more? One more time? Okay, and then the other guy, exactly the same thing, right? D over x minus 3 plus e over x minus 3 squared, and f over x minus 3 cubed. And all of that is equal to 1 over all of that. Okay, and when you're solving for the constants, you follow the next step here, and this would be, it'd be a fun exercise, but let's not do that. Okay, the last thing I want to talk about today is a very important thing that you have to look out for before you jump into the partial fraction expansion. The degree of the numerator must be less than the denominator. Before the expansion. So notice that's the case with every example we have seen today. In the first one, we have a second degree downstairs and first degree up. So the top had a lower degree. And then same thing with the next one and so on. So that's the thing you have to make sure you have before you do any expansion. And when that's not the case, then you got to do something about it. So here's an example. Here we have a second degree on the top and the second degree in the denominator. We have to have the thing on the top with a lower degree than the one downstairs. But that's not what we got here. So when this happens, the simplest way to do that is to do a long division. Let me take the thing on the top. It's x squared plus 0x plus 1, right? And that thing is divided by x squared plus x plus 3. When's the last time you did long division? All right, let's do Okay, so let's divide things out. I need a 1 here, right? 1 times x squared times x times 3. And then we have this thing here, subtracting everything down here. So we get x squared minus x squared. The x squared terms go away. 0 minus x, 1 minus 3. Okay? So what this means is that when you do the division here, you get a 1 here, and then a remainder of this. Equal to 1 plus the remainder over that. And now this remainder here, this thing that's left over, has the right form. The top has a lower degree than the denominator. So in principle, then you would proceed and do the thing you just saw in today's lesson. Now, notice that in this case here, this is an irreducible quadratic. And that's case 3. We'll look at that next time. So on Wednesday, we'll start with what do we do with the irreducible quadratic. Question? What's that? It's on the homework, but they didn't ask you to find the